What is going on, guys? Welcome back. In this video today we're going to cover the most important evaluation metrics for classification, and we're going to also understand how to interpret them. So let us get right into it. Alright, so we're going to take a look at the most important evaluation metrics for classification in this video today, and for this I prepared this Jupyter notebook here with a bunch of code, with some formulas and with some visualizations here. And the goal of this video today is to give you, on the one hand, an overview and a list of different metrics that you can choose from, but also an understanding, an intuitive understanding of these metrics so that you understand what questions are these metrics answering, and also how can I interpret their values. This is what we're going to talk about in this video today. And if you are interested, I also recently made a video like this for regression metrics, so just watch this video if you're interested in that. Today we're going to focus on classification. Now, just briefly, for those of you who don't know what classification is, it is a machine learning task where we're trying to assign instances to specific groups or classes. So for example, we might have, I don't know, different let's say we have different images, and these images can represent a cat or a dog or a horse, different animals, for example, and then taking such an image and determining whether what we see in this image is a cat or a dog or something else. This is a classification task. Whereas a regression task would be asking something like the number of cats in an image, or maybe the price of a house or something like this, where we get some continuous value, and in classification we get classes or groups that we have to assign instances to. So we have images and we need to say this is a cat, this is a dog. Or we can also get text and we have to say this is a positive text, a negative text, a neutral text, basically sentiment analysis. That is also a classification task. So classification is always trying to assign an instance to a group or to a category or to a class, and to say it's part of that and not part of the others. That's the idea. So the code that we have here is not too important in terms of what kind of data we're using. I think this is some kind of forest coverage data set here. So it's not really that important what kind of data we're working with. The important thing is we're doing classification here. Also, the models are not too important. They might become a little bit more relevant when we get to the ROC in the end, because then we have to work with probabilities. So we need models that can provide probabilities. But besides that, it doesn't really matter what kind of model we're using here. We can use random forests, we can use decision trees, k-nearest neighbors classifiers, support vector classifiers, neural networks. It doesn't matter. We just need something that gives us a prediction for a class. So what we have here first is the most commonly used evaluation metric for classification, which is accuracy. And accuracy answers a simple question, which is how many of my predictions are actually correct, expressed as a percentage. So what percentage of my predictions, or of the model's predictions, is actually correct? So if I make 100 predictions, or the model makes 100 predictions, and 79 of them are correct, 21 of them are incorrect, we have an accuracy of 79%. If all the predictions are correct, we have an accuracy of 100%, and if none of them are correct, we have an accuracy of 0%. Now, to understand the formula here, we need to understand that this is, first of all, the accuracy for a binary classification task. So we either have 1 or 0 as a class label. Now, 1 or 0 doesn't have to be 1 or 0 in terms of semantics. It can also be cat or dog. It can be malignant or benign in terms of medical classification. Or in the context of medical classification. It can be up or down, it can be yes or no, it can be whatever you want it to be, but we have two classes, a negative class and a positive class. And what we have here is we have true positives, true negatives, false positives, and false negatives. So to understand this, let's say we do cat and dog classification, and the question is actually, does this image show a cat, yes or no? And no would automatically say it's a dog, for example. So does it show a cat or a dog, expressed as does it show a cat, yes or no? And a 1 would be a positive instance, so it actually shows a cat, and a 0 would be a negative instance, which means it's a dog, so it does not show a cat. Now, true positives are instances that we classified as cats and that are actually cats. And true negatives are instances that we classified as not cats, so as dogs, that are actually dogs. And false positives would be instances that we classified as positive, so as a cat, but they're actually a dog. And false negatives are instances that we classified as not a cat, so as a dog, but it's actually a cat. So that is what these four mean. true positives, true negatives, false positives, and false negatives. And the accuracy now here in terms of binary classification is just all the true classifications divided through all the classifications. So if this is a multi-class classification problem, it would just say correctly classified instances divided by all instances that were classified, by the number of all instances that were classified. And the accuracy really just answers this question. So how many of these instances that I predicted or made predictions for, how many of them did I get correct as a percentage? And this is also what you get by default when you use the score function in scikit-learn. So you fit a model, you fit multiple models, and then you call the score function. If you do that, you get this accuracy score here by default. So knn.score, forest.score, model.score in general will always give you the accuracy score. Now you can see here that if I do this manually, so if I say accuracy knn and accuracy forest by just getting the predictions and summing up all the correct predictions, dividing them by all the predictions, I get the same values then that I get when I call the score function. So this is just the binary classification, and in general it's correct divided by all instances. So we also have something called the confusion matrix, which I want to show you here. And the confusion matrix is not really a metric, it's more of a visualization, you could say, or more of a grid, you could say, and it shows us what kind of classes are being misclassified or wrongly classified as other classes. So what you see here is we have the predicted label and we have the true label. And in this case now the data set we're using here is some forest coverage type data set. And basically we have different kinds of wood or trees, I guess. And what we see here is that, for example, this lodgepole pine, which is actually this kind of tree, is oftentimes misclassified as spruce. So that is something that we can see here. Now the diagonal is not really interesting because these are correctly classified instances, because in this case spruce is classified as spruce, so it's actually correct. But you can see that you have some pretty large numbers here and there. This one is probably the most interesting one, where we actually do have a confusion, a misclassification. You can see that this is oftentimes a problem. A spruce is oftentimes, or I should say a lodgepole is, or a lodgepole pine, I hope this is how it's pronounced, is oftentimes misclassified as a spruce, and vice versa, which is not necessarily the case. So these two numbers here are not the same. This here is this one being misclassified as this one, and this value here is the spruce being misclassified as the pine. So there's a difference here. But this is also a metric that you can look at. This is especially interesting in my opinion if you have, or not necessarily especially interesting, but this is also interesting if you have a binary classification, for example, in the breast cancer data set, where you just have 0 and 1, so malignant or benign. You can see also that we have here this confusion matrix, which includes already the misclassified instances. So we have 35 true, actually what is this? This is true, I think malignant is 0, if I'm not mistaken. So that would be a true negative, this would be a true positive, this would be a false positive, and this would be a false negative. So we have these values that we have in the accuracy formula here as part of a confusion matrix. But let's get back to the metrics, because we do have some other metrics that are not accuracy but are also very interesting because they answer different kinds of questions. So precision, for example, is a metric that is oftentimes used, and what this metric basically tells us is when I classify something as positive, so when I say this is a yes, this is a 1, this is a cat, how often am I correct about this? So it's not about how often do I make correct classifications, it's when I say yes, how often is my yes correct? So you can see I'm taking the true positive and I divide by true positive and false positive. So whenever I say something is positive, whenever I classify something as positive, I want to know how many times as a percentage am I actually correct about this. So how many of my positives are true positives and not false positives. So you can see that if I do this manually here, I get the same thing as when I use the precision score from scikit-learn. And then we also have the other part of that, which is the recall. And this is oftentimes a trade-off here. You want to have precision and recall high if possible, but sometimes it's a trade-off because the recall tells us how many of the actually positive instances do I find. So out of all the instances that should be classified as positive, which are the true positives, the ones that I did classify as positive that are actually positive, and those that I misclassified as negative, but they are actually positive, how many of all these positive instances did I actually recognize? So you can think about it that way. Let me open up a drawing tool here. So my paint. Let's say I have a pool of, let's say I have some wrong instances here, some negatives. And let's say I have some positives here. If my model now says the only one I'm going to classify as positive is this one, I have a precision of 100%. Because every time I said something is positive, it was actually positive. I have 100% precision. Every time I say, yes, this is positive, my precision is 100% because I was right 100% of the time. However, my recall is not that good because I have actually 5 instances. So my recall here would be 20% because I have 5 positive instances and I classified only one of them as positive. So I missed 80% of the data that I should have classified as positive. Now, of course, if I just always classify everything as positive, so I say all of this is positive, then my recall is going to be 100% because I classified all the positive samples correctly. All of these are positive and I recognize all of them as positive. But my precision is going to be worse because, of course, I misclassified these here as positive even though they are negative. So that's oftentimes a trade-off. You need to find a model that can keep precision and recall high. And yeah, oftentimes it's not that easy. Which is why we do have an F1 score for evaluation, which tries to incorporate both precision and recall in the evaluation. And the interesting thing about this formula here, the F1 score, is that the moment your precision or recall is very low, the F1 score is also very low. So to get a good F1 score, you also need to get a decent precision and a decent recall. So we do have the example here as a formula, but let me show you that this is actually the case. If I take this formula here and let's say I have precision of 90% and recall of 90%. And now let's remove this. Let's call this precision. Let's call this recall. Precision and recall. Actually, let me also print the value, F1 tree. I get 90% also for the F1 score. Now, if my recall is 100%, then also my F1 score increases. It's not 100% because my precision is still not 100%. But you can see I get a decent trade-off. If I get to 0.7, my F1 score is quite low. But if I get, for example, to something like 30%, you can see that this drops massively. So you need to have both quite high. You cannot just have one very high and the other one very low. If you want to have the F1 score, if you want to have a decent F1 score, you need to have a decent precision and a decent recall. That's what this score is for. It's balancing these two metrics. Now, we do also have some other metrics here based on the confusion matrix. So based on true positive, true negative, false positive, false negative. And some of them are going to be important for the final metric, which is very important. But we do have here the combinations, the different combinations of these TN, TP, FN, FP combinations. So here we have the recall again. This is also called the true positive rate or the sensitivity or the hit rate. Again, this asks the question, what percentage of positive instances did we recognize as positive? This is the recall. Again, remember we had the dots. If I recognize all the green dots as green, it doesn't matter how much I misclassify all the other dots, but I want to find as many of the positive instances as possible. Everything else is irrelevant if I want to increase the TPR, the true positive rate, the recall. Then we also have specificity, which is basically the same thing for the negative instances. So Maybe to give you again some visual stuff here, I think it's always easier to understand it that way. Let's say I have some positive instances. Let's say I have some negative instances. And again, if my model now goes, this is now, again, for the first one, the recall, I want to have these recognized. It doesn't matter if I recognize all of these as positive, my recall is 100%. This is the same thing that we talked about before. And now my true negative rate is the same thing, but for the red dots. So if I classify all of these here as negative, I covered all the negative instances, which means my TNR, the true negative rate, or the specificity, is 100%, because the important thing is that I classify these here as negative. It's basically the same thing as the recall, but the recall focuses on classifying the positive instances, in our example, the cats, and the true negative rate focuses on the dogs, so to say, or the not cats. Then we also have the PPV, which is the positive predictive value, or the precision. And the precision is, again, what we said. If I classify something as positive, how many times am I correct about this? So if I classify exactly these here as positive, my precision is 100%. If I classify these two as positive and all the rest as negative, my precision is also 100%. It only matters how many of my positive predictions are actually correct. And the same thing is also true for the negative predictive value, which is the same thing for the negative instances. When I say that these two are negative, everything else is positive, my NPV is 100% because I'm correct 100% of the time for negative instances. Then we also have the false negative rate, which asks what percentage of positive instances did we misclassify as negative. So if I take the positive instances, you can look at the formula true positives and false negatives. So these are actually positives, and let's say if I do it like this, these would be my true positives, and these would be my false negatives because I classified them as negative, but they're actually positive. The question is, what percentage of these were classified correctly? So in this case, 3 out of 5 would be, so 3 divided by 5 would be the correct answer, or actually the opposite, sorry. This is the false negative rate, so it's the opposite. It would be 2 divided by 5. That would be my false negative rate. How many of them did I misclassify as negative? Same thing goes for the FPR. The false positive rate would be the same thing, just with the red instances, with the nose, with the dogs, so to say, just the other way around. And then we also have the false discovery rate and the false omission rate, which is when we classify something as positive, how often are we wrong about this? You can think of this to be the opposite of the precision. So I classify something as positive. How many times am I wrong about this? 0% of the time. How many times am I wrong about this? 100% of the time, if I do it that way. And the exact same is true for the negative classes. So just swap the colors, swap cat and dog, and then you have the FOR. So I hope this was not too fast, this was not too quick, but that is basically what these metrics are for. And the two important ones, to just mention them again before we get to the next one, is we want to have the true positive rate and the false positive rate. So we have the TPR and we have the FPR. Again, keep in mind, TPR is recall. What percentage of positive instances did we recognize as positive? And FPR is what percentage of negative instances did we misclassify as positive? And these two are, of course, a trade-off. The one thing is I want to cover as many positive instances as possible, and the other one is I want to not misclassify stuff as positive. So again, I'm going to open up my paint. The more often you hear something, the better. So if I have, again, some dots here, like this, and I have some, where's my red? I have some dots here like this. To maximize my recall, again, I can just classify everything as positive. Then I have covered every positive sample in here. This would be the trivial way to increase my recall, my true positive rate. But of course, I also want to keep my false positive rate low, because in this case, what percentage of negative instances did we misclassify as positive? also 100% because I misclassified literally every negative instance as positive. So I want to try to maximize my true classification. I want to maximize finding all the positive instances, but I also don't want to misclassify negative instances. So of course, if the model is perfect, it's going to have 100% accuracy, and it's going to say, okay, I can recognize all the positive examples and or all the positive instances, and I can also not misclassify any of the negative instances. That would be perfect. But oftentimes it's a trade-off, and we're going to see that trade-off in the so-called ROC curve, in the receiver operating characteristic curve, or also in the area under the curve. So what you see here is you have the true positive rate and you have the false positive rate. And the idea here is that we have probabilities for, or our model doesn't just say it's this class or it's the other class. It doesn't just give us 1 or 0. It tells us the probability for 1 is that and the probability for 0 is that. So it basically tells us, I do have a preference, but here is my estimation. Here's my probability that I can give to you. And we can adjust a threshold to say, okay, if there's at least this probability, I'm going to accept this as a true, or I'm going to accept this as a positive. Otherwise, I'm going to accept this as a negative. And what we can see here in this ROC curve is the trade-off between, or the trade-off that happens when we adjust that threshold. So to understand this graph here, in the bottom left, we have a true positive rate of 0. I don't recognize a single example here as positive, but I also don't misclassify any example that is actually negative as positive. This would be equivalent to just saying all the instances are negative, so I cannot make any mistakes. I cannot misclassify any negative samples, so my FPR is at 0, but also I don't recognize any of the positive instances, so that is 0 as well. The other extreme is when I say everything is positive. In this case, I recognize all the examples as positive, but I also misclassify all the negative examples as positive. So I don't want to be here, and I also don't want to be here. The magic happens here. You can see that this is a good model because I can get a pretty high, in this case something around 0.87, I guess, something around 0.87 of true positive rate, so I can cover 87% of all the positive instances. I can recognize them as positive without misclassifying a single negative instance. You can see I'm still at 0 here, so I can get a 87% coverage or recall without misclassifying any of the negative examples. However, if I'm willing to tolerate some misclassification of negative examples, I can even increase my recall. So by allowing for I would say this is something like 0.04, maybe, something like this. If I allow for 4% false positive rate, I can increase my recall to around, I would say, 0.92 or something like this. And if I now take the whole area, if I take more or less the discrete integral, we could say, of this curve, so if I take everything that I have below this curve, I get the AUC, the area under the curve. Now, if my model is perfect, I'm going to be able to classify, I'm going to be able to get 100% recall and 0% false positive rate. This is what I talked about in my paint. But if my model is not perfect, if there's some overlap, I can make a trade-off here. Now, sometimes it's just not possible to find a perfect solution. Again, let me open up my paint. If I have, let's say, a single feature that I'm looking at, so this would be my one feature, and let's say I have some distributions in here, so I have some distribution of this feature, and these are all my negative examples. And then I have another distribution, let's say this one here, and these are all my positive instances. And now let's say I want to have 100% accuracy when I do the classification. It's not going to work because there is a certain overlap here. So I have to decide, okay, if the feature is here, I'm going to just say it's positive. In this case, I would have 100% recall. I would recognize all the positive examples, but I would also misclassify a lot of these negative instances. Whereas if I say I want to have the threshold here, I'm going to have a worse recall because I only recognize these here. I miss out on all of these, but I at least have a false positive rate of, I mean, I would have to put it here, but then I have a false positive rate of 0. So oftentimes it's not possible to have a perfect model. And in this case, of course, we would have to work with a trade-off. So we have to decide, okay, do I want to tolerate a little bit of a false positive rate, or do I want to tolerate a little bit of less recall? And the overall area under the curve tells me how well my model performs. In this case, we have 0.99, which is close to 1, which would be perfect, and this signals this is a pretty good model. Now, if I go down here to this example where I train a decision tree classifier, we can see that the ROC curve is not that good, so we don't cover as much of the space here, and we have a ROC-AUC score of 0.88. And here we even have 0.82 if I just allow for a single feature. So this is a very important metric, and you should be able to understand what this graph means. Again, let me repeat it. You're trying to find a trade-off. You want to find as many of the positive instances while not misclassifying or misclassifying as little of these negative examples as possible. So here, maybe you would decide to go with this point because here you get a decent recall, something like 0.95. But you only have to allow for a little bit of misclassification of negative instances. Whereas if you go to the right here or even here, you would not really get much of an increase. Maybe you get 0.02% more recall, or actually 2% more recall, but you massively increase the misclassification rate for negative instances. So this is what you're looking for here. Yeah, so these are the most important classification evaluation metrics. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching, see you in the next video, and bye.